I'd reduce this, divide everything by 4, gives me a 3x squared negative 21x plus 26. 0 divided by 4 is also 0. That's legal. That's the reason it's legal, is because I did 0 divided by 4 as well. This is a quadratic equation. We've got to solve it equal to 0, so it goes back to that same. You can try to factor it. Real world, nothing factors. You know, we spend so much time working on factoring, but if you're talking about a real world application, this ain't going to factor. You're going to have a decimal value that's going to give this an answer of 0. So real world, you're going to have to use quadratic formula. Negative b plus or minus the square root. I always like to do this over to the side. B squared. I'm going to go ahead and do the whole thing. B squared minus 4 times a is 3 times c is 26. Gives me 129 over 2a is 6. Remember your domain restrictions. I don't know that you're going to get 2 different answers here. You might just get one, because sometimes you'll have like 21 minus. If you do a square root there and you get a negative, x can't be negative. You can throw that answer out. This one, well, you know what, I can already look ahead and I know why, but this one will give you 2 answers. So we got 21 plus root 129. Let's do that one first. I'm getting a little bit of a glare. 21 plus the square root of 129. I like to go ahead and enter there, divided by 6. Gives me about 5.4, and it says round your answers to the nearest hundredth, so I need 2 decimal places, so 5.39. Or we got to do 21 minus root 129. 21 minus the square root of 129 divided by 6, enter, gives me 1.61. So that's the x values that will give you the smallest, the largest possible volume. So let's actually plug these in and get dimensions. Those are my x values, those are not my dimensions. So when x is 5.39, it gives us, and I should have left that as exact here. Well, you know what? My bad. Throw that one out. X can't be 5.39. Does everybody understand why? X has to be between 0 and 4. So I could have automatically thrown that out. So now when x is 1.61, I have 8 minus 2 times 1.61. That gives me 4.78. And then 13 minus 2 times 1.61, which gives me 9.78. So the dimensions of the box, and we do need that x value because the x value is right there at 1.61. The box that will maximize volume is we're going to cut 1.61 out of the corner, and it's going to give us a box that is 1.61 by 4.78 by 9.78. It will ask you for the maximum volume. So once, I'm not going to work through it, but in order to find volume, just a reminder, you do length times width times height. Those 3 numbers you're going to multiply together. That'll give you the box of maximum volume. Okay, on the next one. It says 2 sides of a triangle, and it does not say right triangle. It does not say a cube of 2. 2 sides of a triangle are 12 and 6. The angle between them are theta, or is theta, excuse me. And we're wanting to know, should I make theta really small or really big in order to maximize the area of this triangle? I need to know the theta that's going to give me the biggest possible area here. Now, let me explain one thing. You could plug and play here. You could plug stuff in here, plug and chug, and try to kind of find something out. But again, what if your theta is like 87.36 degrees? You can kind of narrow it down to where it's between 87 and 88, but in order to find the exact, you're going to have to use this process. Okay, so here's something you probably don't remember. How in the world do I find the area of a triangle if I'm given a theta? There's a formula let's see, if you've got a triangle, might not, like I said, you might not remember this from pre-cal, but let's say that, again, this is theta and this is A and B. And formulas like this, I'm not going to expect you to memorize. I would give you this formula on the test if you needed it. But now if it was the area of a regular triangle, no, I'm not going to do that. The area of this triangle is 1/2 AB sine theta. So that's an area formula that actually involves two leg lengths and an included angle. 1/2 times this leg times the sine of the included angle. So honestly, this is probably the easiest problem we've worked today. Let's think about our restrictions on theta. I know that theta has to be bigger than 0 because obviously you can't have a triangle if theta is 0. It's going to be a straight little line. And theta, this could be an obtuse triangle, and theta could be huge. So theta could be up to 180, not including 180. It could be 179.9. I don't think that's going to be the right answer because then you got this really skinny triangle with not much area, and we're trying to maximize area. So, but it could run anywhere between 0 and 180. So that's where you're looking for your maximums here. This is very important in a trig problem. The reason why that is important because hopefully you remember that if I have something like sine of x equals 1/2, that has millions of answers. I would really like to narrow it down to where there's only one or maybe 2 answers, not millions. So this is very important that you restrict your domain, that you figure out what values of theta can my problem actually have. So here we go. The area, we need to, in order to maximize area, we need a formula for area. So the first step is to actually write you a little formula. What's the relationship amongst these values? And it's right here. Area is equal to 1/2, and I'm going to plug it in first. 1/2 times 6 times 12 times the sine of I don't know theta. That's my variable. That's my changing value. And we clean it up. 1/2 of 12 is 6 times 6 is 36 sine theta. So if I knew what theta was, I could actually plug it in right there and I've got the area. But I don't. We're changing theta. We're trying to figure out what values of theta would give me smaller or bigger areas. So here we go. We're going to actually find the derivative, and we are finding the derivative with respect to theta because that's my changing value. That's what we're looking to change here in order to get these different areas. 36 is a coefficient. Bring it down. The derivative of cosine or sine is cosine, and we do not have to use chain rule because it is theta, and it's a clean theta. So here is what we're trying to maximize, or excuse me, here's what we're trying to figure out is equal to 0 or undefined, which will maximize hopefully this function. Like I said, this is probably the easiest one on here. So between 0 and 180, I've got to figure out where's this undefined. Nowhere. It's continuous. It's a cosine curve, or where it's equal to 0. So we come over here and we set it equal to 0, divide by 36. We solve it. Simple trig equation. Where is cosine equal to 0 between 0 and 180? That's only on from here to here. And I know that cosine is equal to 0 at 90 degrees. So I've got a critical value at 90, which actually makes this a right triangle, and it makes it really easy to find the area of. You really don't have to use this formula anymore if you don't want to, but to find the maximum area, it's going to occur at 90 degrees. You can plug it in now. The sine of 90 is 1, correct? And the area would be 36 times 1, which is 36. That's your maximum area. You can try different degree measures, but that's going to be the one that gives you the largest area possible. Okay, here's what the problem says. You've got a right triangle whose hypotenuse is root 15, and it's revolved around one leg in order to generate a cone. So what we're going to do, we're going to take this entire right triangle and we're going to revolve it like this right here around one of these legs. We're going to spin it around, and notice it's going to form a cone. If we trace its path, you now have a cone. which looks, we all know what a cone looks like, to where the height of the cone would be the exact same thing as the height here of this triangle. The radius of the cone would be the same thing as the width here of this. So I'm going to call this H, we'll call this R. We want to know what H value and R value would maximize the volume here. Let me remind you of something. Use as few of variables as possible. I don't want R's and H's. If there's somehow that we can define R's in terms of H or define H in terms of R's, let's do that. Because right now, here's what we have. Our volume formula, if you don't remember, 1/3 pi r squared, where r is the radius of the base, times the height. The way I told you to remember that in geometry is find the area. If it comes to a point, find the area of the base, multiply it times the height, and then take 1/3 of it. And that's what we've done here. 1/3 of the area of the base times the height. But if at all possible, we want to try to somehow get rid of either an R or an H and just have just R's or just H's. There is a relationship that we can see here between the R's and H's, and it is the Pythagorean theorem. H squared plus R squared equals the square root of 15 squared. You'll see that? That connects H's and R's. So now if I use this, I can somehow get rid of one of these, and it's, watch this, it's actually going to be a little bit easier to get rid of R squared because look, I can move H squared over and say R squared is 15 minus H squared, and instead of solving that again for R, just go ahead and plug it in. There's R squared. Plug this in for it. Makes the problem a little bit simpler. Volume is equal to 1/3 pi. Instead of R squared, I now have 15 minus H squared times H. So since I did have that connection, I could somehow get rid of a variable. If you didn't have this, it would have been impossible. You'd have two different variables. And that's a little bit deeper. Let's clean this up some. Volume is equal to 1/3 pi. Distributive property would be, I'm going to put my h's first, negative h to the third plus 15h. There you go. That's what I'm trying to, that's my volume. Okay, if I've got a height, then I can plug it into that, and I've got my volume. I don't need a radius anymore because, again, I eliminated that variable. I want to maximize this, and again, let's talk about restrictions. H must be greater than 0. And is there, yeah, there's one more. In this right triangle, this is called, again, the hypotenuse. The hypotenuse is always the longest side, so we know that H can't be longer than the longest side, so root 15. It's somewhere on that domain. So look for anything. Is there any values that would restrict domains? That's very important to do first. Okay, since we're trying to maximize, let's find the derivative. I'm going to call it dVdh again. Finding the derivative of the volume with respect to height, because that is our variable here. I want to remind you that anytime you have, this is simply a coefficient. You could distribute out if you want to. I don't really want to. I just want to copy it down. 1/3 pi, and then put you some parentheses. Okay, anytime you have a coefficient, not a constant would be 0, but if you were to multiply this out, this stuff is just being multiplied by this, bring it down. And find the derivative of the rest of it. Negative 3 h squared plus 15. I might actually clean it up a little bit if I did distribute that out, because 1/3 times negative 3 would be negative pi h squared, and 1/3 times 15 would be plus 5 pi. That'll work. And we want to know where is this derivative, 0 or undefined. It's never undefined. We're good on our interval. It's never undefined. There's no fractions, there's no radicals, there's no tangents, there's no anything that's going to force that to be undefined. So therefore we simply set it equal to 0 and solve it. Because critical values occur, again, I've said this several times, critical values occur anywhere, that's pi, anywhere the derivative is equal to 0. I would reduce this before I started, divide everything by pi, gives you negative h squared plus 5 equals 0. Looks a little bit better. Subtract 5 gives me negative h squared equals negative 5. Divide by negative 1 gives you h squared is 5. So h is equal to the square root of 5. You do not have to worry about plus minus, because again, h is between 0 and root 15. You cannot have an h that's negative. So that's going to be my height that maximizes volume. In order to find the radius that goes along with that, because they're going to ask you for it, just go back here. Because we know that our height, this is where the maximum volume is going to occur. So Pythagorean theorem, you got root 5 squared plus r squared equals the square root of 15 squared. Subtract 5, you get r squared is 10. And we know the radius also is restricted to only positives. So the radius would be root 10. There's 2 of my answers. And then if it asks you for the maximum volume, we can plug the root 5 back in here. And that's going to tell you the volume that's actually going to maximize.